Hi everyone, and welcome back to C Sharp Corner Live Show. As always, I'm your host Stephen Simon, and we're back once again. This week we are back with C Sharp Corner MVP Show. And as always, if we are live on Wednesday, it means we are streaming C Sharp Corner MVP Show. There are many other live shows that we do at C Sharp Corner. Just go ahead and visit C Sharp Corner. I think it's csharpcorner.com/live. I think yeah, that is the URL. So welcome back once again. I'm a little gloomy today. You can see from my eyes I've been working a lot. So yeah, I'm really excited for this week episode because back to back we have the guest joining us from Ukraine. Last week we had Vitali, and this week we have Bohdan joining us. He's joining us for the second time, and he has more than 5 years of experience. Definitely, I think he has more than that. He needs to update C sharp on the profile. I think so. He probably has more than 5 years of experience. He works on databases, design patterns and practices, and yeah, his articles have been read more than 200,000 times on just C sharp on the itself. So. Yeah, I'm really excited to host him today. So, without any further ado, let's bring our guest in. Hi, Bodan. Welcome to C Sharp Corner MVP Show.
Hello, thank you for having me again. I'm really
So,
excited to be here.
Bodan, once again, thank you so much for accepting the invitation. I know you're joining us from the tough times and also from the tough location. So, thank you so much for your time. Really appreciate it. So, just quick update for all the folks who might be interested in watching us the live show. I know you're joining us from Ukraine. How is life there? How's your life changed, and how you have coped up with last 4 to 5 months?
I mean, this is the thing that really depends on the region where you reside in, and some regions are pretty fine, but for the first couple of weeks I've been in Kiev, and these were really, really tough times, and, had to adjust to that and, to the sense of danger. But eventually you get used to it and you get used to everything. And it's worth mentioning that the war here is like for 8 years, so eventually we've got used to that, and now getting used to even more danger. Uh, But it's yes, I'm alive, and that's the
Yeah.
great thing for now.
Yeah, I mean, our hearts goes out to all the Ukrainians, and thank you once again. So, Bodhin, looks like today you're going to talk about your daily application performance, right? For all the folks who are joining us right now, would you like to give a quick overview on what it is so that everyone can stick around?
Okay, sure. The thing about this talk is, a lot of stuff about performance looks really sophisticated, and I've came up with the idea to talk about performance in the same way, in the way in which, like, every ordinary developer that doesn't deliver, like, some rocket science, but writes an ordinary code, this developer can write performant code as well. And I've gathered different stuff, different advices from my career, from code that I reviewed, and all the examples in this presentation are actually are real life examples that I've encountered myself. And this is our they might look basic, but that was the thing, to show some stuff that everyone can use to write performant code.
Wow, that sounds very exciting that you have picked all the things that you have learned while working on different projects and the problems that you have faced, and you have collected into one presentation. So I'm really looking forward to it, Bodhin. So please feel free to go ahead and share screen, and then I'll put it into the live stream. And everyone who's watching, please feel free to go ahead and drop your questions in the comments or how you feel about the live show. We'll make sure that we answer towards the end. I know it's a little late here in India. It's almost night time, but never mind. Let's see.
Okay, so at this point I'll start sharing my screen. Okay, let's do that. And here is my presentation. Wait a second, it takes time to load. So as
Yeah.
Simon already mentioned, it's called your daily application performance, and we'll hide this one. And also, Simon did already a great introduction for me, so I won't talk much. The only points I wanted to highlight that the surest way to reach me out is on Twitter. And also, this presentation is really code intensive. So, in case you want to follow along, or in case you want to check out the codes later, here is the link to the GitHub with all the examples I will be showing today. So, as I've already mentioned, a lot of stuff about performance is really advanced. For example, there's except from the article which suggests you to align your operations in your code in such a way that it has more L2 cache hits of your processor, and this looks a bit intimidating. Or for example, that in order to write performant code, you should take advantage of pinit object heap internal. This is a special garbage collector feature. Or for example, some unmanaged code that is also hard to support and hard to figure out and hard to write correctly. So in such a case, you might have, all these things, they have their notion. For example, if you write in the library, which needs to be super fast, or for example, if you're a top performer that serves billions requests per second, then you need such things, and they are necessary for you. But a lot of folks, and personally me, we are writing just simple line of business code, and when reading this stuff, you might think that, oh, in order to write performant code, you have to be like this guy. So either you're this guy or you just don't write in performant code. But to be honest, this is not actually true. And I wanted to mention the book which is called Continuous Architecture in Practice, which states that when you're designing your system, you should focus on your non-functional requirements first. These are key drivers for your system. And performance is one of these drivers. So actually, performance matters for any system, not just for top performance or for some top-notch library. So the question arises: how do you write performant code for simple systems? And since I've started my talk a bit on contrarian, I will go on with a bit of unpopular advice, but maybe the most working one. And here it is. And the thing is, I'll explain my thinking. The thing is, that often hardware is just cheaper than software developers' labor. And, we are engineers, we just want, to solve advanced issues. We want to try that pinit object hit or something like that. But sometimes, at least on the early stages, it's easier just to add more hardware to make things work faster. And the other thing worth mentioning that these days a lot of attention is devoted to writing software in scalable fashion. But again, when the issue comes to improve the performance, we sometimes do forget that we have written software in such a fashion, and we trying to to do that these advanced things, but we can just take advantage of the ability of the software to scale. And to prove my point, I'll tell you a story from personal experience. A couple of months ago, we have written quite a sophisticated logic that does aggregation based on Elasticsearch. And this logic was such a sophisticated that it failed with a timeout on a testing environment. So personally, I've spent like a couple of weeks to fix the issue. And after I thought I was done, it turned out that I wasn't done. And after that, we had to spend a couple of more weeks to fix the issue. And we added quite a complex logic to do that. But when our CTO asked us about that, the first question he asked is how much resources basically consumes Elasticsearch on testing environment. And we've answered this was 16 gigs of memory on one node cluster. And the thing is that Elasticsearch itself is the NoSQL storage, and it is designed to scale. It is intended to scale. So it should be deployed on nodes with on a cluster with multiple nodes with a decent amount of memory. And the moral of the story is that actually our company spent just a couple of $1,000s to do some complicated code and to mitigate the issue that even wouldn't be reproduced on the production environment, because production environment has a decent amount of resources. But again, the thing might be unpopular, and the thing with it that when someone listens to this, he might think that, okay, at this point I can write just bad code, and I will just get away with it with throwing more and more hardware. That's, of course, this not like things should be done, and of course at some point you shouldn't be writing reckless code. And the rest of the presentation will be real world examples of some reckless code that I found myself, and also some things how to remedy that reckless coding. And we will start, from the top to bottom. We will start from the more high level concepts, and we'll end up with a bit low level concepts. So here's how you can improve performance of on the layer of your architecture. Here are the couple of options. We will talk briefly about each of these options. So when it comes to microservices, the main benefit is that microservices allow you to scale different parts of the system horizontally, which means that you can fine-tune the performance of your system in these places where you actually need this. And the things come to extreme with the serverless architecture, since serverless architecture gives us promise of scaling up with no provisioning costs, scaling up almost immediately. And this is pretty fine for for unexpected loads. But again, this thing comes with a pinch of salt, since nobody loves to have a distributed spaghetti. Thing about this, if you just have a purely organized code that looks like spaghetti code and you split it into microservices, then you have the spaghetti that's the same spaghetti code, but it is multiplied by the complexity of distributed system. And the thing is with the distributed system that it is really hard to write correctly the distributed system. It requires discipline, it requires organizational capability. So you shouldn't just split your stuff into microservices because you just want to make your code better. Your splitting should be dictated either by your architectural need, like scaling, or by your organizational need, when you need to make it to enable writing your software in parallel by different team, for example. Regarding the data partitioning, this is quite a broad topic that deserves additional presentations, so I won't talk much about them, but the key thing is to split the data in your database server into different parts, and depending on the algorithm, how do you split them, either by geographical region or by some artificial key, or either this is some just a copy of your server. This is all the different all the flavors of data partitioning. When we talk about asynchronous communication, here's the quote from the book with enterprise integration patterns, which states that when parts of your system communicate synchronously, there is a coupling that is created between them. And actually, this means that the producer has to produce messages with the same pace that consumer consumes them. So when you split this and you use asynchronous communication, each item can work at their own pace and speeds things up a little bit. And here's another example for you. Let's have a look at the following system. We have two modules. One module sends the file, and after the file is successfully persisted, and only if the file is successfully persisted, we save the metadata file. But what actually happens on the receiver service is that we are not only doing persistence, we are also doing some processing. So there are two things that worth considering here. One of the things is that the synchronous communication is inevitable at that point, since we can only send metadata file after we're guaranteed that we persisted our main file. And the other thing that we have additional wait. We have actually to wait for the processing to happen, and that might take a lot of time. So in order to mitigate that, we might do the processing in the background. For example, we can send a successful response once the file actually persisted, and then we can do the processing in the background after receiving the message. We're leveraging the message architecture here. And this thing minimizes the surface of synchronous communication, which speeds things up a little bit since the sender doesn't have to wait anymore for the processing to happen. And the other thing that I wanted to mention here, and to highlight my point that I mentioned with microservices, is that as you can see, both the processor and the repository are inside the same process at this diagram. Again, this is because writing distributed systems correctly is hard. And if it is possible, you better should avoid it. But for sure, in case that you need to scale your repository independently or your processor independently, and you really have architectural need for that, you can do that as well. In such a case, you split those two items into different processes. You can see on the diagram repository is scaled a bit more than processor is. And this is another way how you also can handle the things. So you can see that we're trying to minimize the surface of synchronous communication as much as possible in order to reduce that coupling. That's it regarding this asynchronous communication. Let's talk a bit about caching. What is important to understand that always the part that consumes the most, that sucks up the most performance of your application, is input-output operations, because talking to disk or talking to network will be always slower than talking to the memory. So caching allows you to replace this I/O operation with in-memory calls to speed things up. And when you do caching, you should consider some of the things. These things are cache hit frequency, which means that actually you're having some amount in memory occupied, for example, with data that otherwise would be persisted in TB. And you should really be sure that there is a point in that cache, that it is hit quite enough in order to really be useful and not just to suck up some memory. And also some such things like size and expiration, which bring you to the understanding about the eviction strategy from the cache. I mean, if the items are not expiring from the cache, you will just end up with this sort of memory leak. And nobody wants to have a memory leak inside your system. And in order to get a better understanding of these concepts, let's have a look at some code. Okay, well, I'll be doing the talking. Let's run some benchmarking. The thing why I'll be running a lot of benchmarks is because when you try or where you write in performant code, you shouldn't be making a lot of guesses, even educated guesses. You should be really pragmatic and you should measure things in order to really be sure whether they're suited for your system or they don't suit for your system. Okay, let's have a look at the example. So the example is as follows. We are scanning the directory in order to get some files. After we're done scanning, we are persisting these files. So what we actually do, we are saving them inside the database via repository, and after that we are copying them to some permanent location. And it's important thing to notice that actually copying happens here, which means that once we add more and more files, we will not only scan these files, but we will also scan prior files, which means that we will have to do a lot of wasteful computation unless we will find the way to avoid those computation. And let's imagine, for the sake of our example, that new 50,000 files per day arrive, and we expect the system to work for 3 years. So at the end of the 3 years period, there will be a lot of files. And let's see how we actually will try to avoid that issue. What happens inside the scanning, that actually we're reading the files from directory. We're adding them in some sort of batch, but just in case if the file is not already processed. So this is pretty good strategy as soon as we can just check whether the file exists inside the database. If it's not, we will process it. But again, talking to database is the I/O operation, which might be pretty costly. When we are speaking about 50,000 of materials per 3 years, it's nearly 1.7 million materials after 3 years. So you just don't want to query the DB with such amount of data each time for each file. And in order to not to do this, in order to reduce those input output calls, we may come up with a cache. We may have a look whether the file exists in that cache. If it exists, okay, we just say that the file exists inside the cache. If it's not, we add it to the cache and we say that up to that point there was no file in that cache. And let's have a look how the cache is implemented. It's nothing quite complicated here. Is the underlying hash set which we utilize, and we just check whether the hash set contains that value. And regarding the expiration and the eviction and the size of the cache, here is this strategy is pretty straightforward. If the count of items in cache exceeds the maximum capacity, then we just stop adding items to the cache. And here is our cache capacity with 1.7 million items. So let's see how we got this figure, and let's see whether this is really sufficient strategy for doing the caching. So in order to check this hypothesis, we will do the benchmarking, which I have already run. So we're creating the cache, and here's the figure. Actually, as I've already mentioned, it's 50,000 of items per day for 3 years. This is 1.7 millions. So we're just adding 1.7 million items inside the cache, and we are using the memory diagnoser feature of benchmark.net in order to see which memory footprint this cache adds to our system. And here's the result. You can see that after 3 years, our system will allocate additional 300 megabytes of memory, even less than 300 megabytes of memory. So, in my opinion, this is a piece of cake for every modern computer, even for my laptop. Nothing to say about enterprise system, where you are, which you are, which we are modeling here. So this looks like pretty good strategy since the cache is hit a lot and it's pretty memory efficient. It doesn't occupy too much memory. Now let's dive into a bit more sophisticated examples, since again it covers caching, but it just covers some other things like lazy evaluation, for example. Okay, lazy evaluation. This one is a lead code item. It's not something like you always do in your line of business code. But this one, it really fascinated me, and I guess we can find some learning from this one. And here's what it is. It's a fancy class which has a method which does appending an items to it to the class. It has another method which increments all existing values inside the class, another method which multiplies all existing values inside the class, and also the method which gets the item by the given index from this class. So here's the example of what's happening. We are adding an item, then we are increasing it. Afterwards, we are adding another item. Afterwards, we are multiplying all of the items. Then we are evaluating our item. Again, we are increasing all items. Then we are appending another item, multiplying all of them, and evaluating all of the three. And here are some constraints, which are the maximum number of operations, the maximum amount of item and of the operand, which actually already are constraints of our system that we can further check when we'll talk about the caching. And also another point that I wanted to mention, that in this case, number of read operation which are get indexed surpasses the number of mutation. This is important piece because it will actually mean that in case we will want to leverage our cache, actually it will make some sense because our cache hit will occur pretty often. So the thing with that we can go on with naive approach, which is explained in the example, that each time we are doing a mutation, we are doing all the necessary calculation. But the thing is that we might not need all the items to be evaluated, which bring us to a lot of wasteful computation. And the alternative would be to evaluate each item lazily, just when it's needed. Evaluate each item when getIndex is called. But then another thing might happen, that we might call the same item a couple of times, which will lead us to evaluating the same item again and again. So in order not to do that, we have to develop a cache which will contain all the evaluated items. So here is how this looks. Again, we have the list of items, we have the list of operations, and we have the cache that already mentioned, which contains all the evaluated values. So when you're doing append, you just add an item to the list of the values. This is pretty straightforward. But when you're doing your mutation, instead of evaluating all the items, you just add the items to the array of the evaluations of the operations. And you have to clear the cache, since at this point your cache becomes ineffective anymore. You have to reevaluate all your items. And this is important part because here where our constraint kicks in, that you have number of reads surpassing mutation, because otherwise our cache would be ineffective. Again, here's the mutation with a similar principle. And when you do the evaluation, you'll try to find the item inside the cache. If you find, you're golden. If you don't find, you evaluate it with all the operations. You apply all the operations, and then you add the item to the cache. Again, we need to be pragmatic. We need to be measure things. So in order to measure things, let's have a look how the maximum possible cache, how much it will occupy. Again, we're using memory diagnoser, and the maximum possible cache will be in the following scenario. As you know, the maximum number of the operation is 100,000 operations. You can find it here. Okay, and the maximum capacity of the cache will be in case when the first half of all the operations would be appending operation, and then we will evaluate each and every item inside the cache. So that every item will be put into the cache. And in such case, our cache will occupy 300 megabytes of memory. Again, that is even easier than in the previous example. Okay, that's it about the caching. Another important thing that is worth mentioning, that in examples I've highlighted, we work with the idea that our system operates on a single node. So the cache resides into the memory of that node. But when we have multiple nodes, when we have systems scattered across the multiple nodes, this is not an option, because when the cache inside the memory of one node is updated, you have to somehow synchronize it with all the other nodes, which requires quite complex choreography. So in such a case, you might have a in-memory storage, because in-memory storage is a bit faster than the persistent database. In my example, this in-memory storage is a Redis, and all the nodes communicate with that in-memory storage to use it as a cache. So actually, this adds some latency, because you have to talk with that in-memory storage over the network. But again, it is better than have some quite a complex choreography between nodes. Okay, let's move to a bit of less high-level concept and more low-level concepts. And one of such concepts is batch processing. When you have a big amount of data, in such a case, it might be impractical to deal with the data item by agonizing item. On the other hand, it also might be impractical to deal with all the items at once, because when you're dealing with a large amount of data, they won't just fit inside your memory, and it will just cripple your system. So in order not to do that, you have a batches of some reasonable size, and you read batch by batch from your data storage and process those batches. One of the examples how you can do that is when you're paying enough attention to the signature of your methods. Some of your methods might return type of enumerable of t, and the other one might be the arrays of t, or for example, the list of t. And the thing with enumerable that actually it allows you to enumerate your things, which means that you can get them as you need instead of getting them all at once and loading them all into the memory, which again will cripple your system. So let's have a look how this looks in practice. This is the only benchmark I want to run because it runs really for a long time. You just have to trust me. Instead, I'll run this one because this one also takes a lot of time. So let's have a look at the other example, which highlights the enumerate files. What happens here is that again we're reading the files from the directory, and we're using standard method which returns the array of strings. So this actually suggests us that all the files inside the directory will be loaded into the memory. Not the files, but the paths of this file, to be precise. But anyway, if you have like 200,000 files inside the directory, this may cripple your system. And after we are done loading, we processing these files. So how can we remedy this in order for this code to be able to work with the directories with huge amount of files? You can see that here, instead of using get files, we're using another standard method, enumerate files, which actually returns enumerable. And after we get that enumerable, we are enumerating it inside the for each cycle. So actually at this point, we're getting our items one by one, and we're adding them to the collection, which is called file to process. This collection has the batch size of 10,000 items. So once the batch is full, we are processing these items. After we've done enumerating our files and we have some files that are left unprocessed, we also are processing them. And since I've told you that I won't run this one, you just have to trust me that on 200,000 files inside the directory, the difference in execution time and both in memory allocation looks really dramatic. You can see this on this figure. And again, if we will revisit our cache example, then we might notice that there we also leveraging this concept. Again, instead of loading all the 1.7 millions of files per single go and checking whether some of them were processed, we're having the batch of like 100 files, and we're enumerating items one by one. After the item is enumerated, it is put inside the batch, and the batch is executed. So again, it's quite the same concept here. And the other thing about batch processing I wanted to mention is that it might not be quite obvious that when we comparing stream to byte array, that actually we are operating with the same concept, and that actually when we're dealing with byte array, again we have to load the contents, for example, of our file into the memory at once, while when we're dealing with the stream, we have the possibility to do some sort of batch processing. So this doesn't look pretty obvious from the signature, but actually this is quite the same concept. And let's have again look at the practical example how you can actually do that. The example is as follows. We have the file, which does a simple file with the sounds, and we are calculating hash on that file. And we have two ways to do that. One of the ways is that we are using standard method file readable bytes, which returns byte array, and the other one is that we're using file stream. We are again this is standard API, which tells us file open read, and we are using that file stream to calculate the hash. So both of the methods inside utils are pretty similar. We are instantiating the MD5 hash algorithm, and it has two overloads actually. One of them accepts byte array, and the other one accepts stream. So actually they're pretty similar. And after we're done, we are fast forwarding to the beginning in order to be able to do a calculation once again. And when we will look at the benchmark results, we might see that both items they are performing pretty similarly in terms of time. Even byte array performs a bit better. So it's in case of just raw performance, it's even better to load the items at once in case they are not that big. But you can see dramatical difference in the memory allocation. You can see that when we're talking about the memory allocation, that way a lot of more memory allocated in case you're reading the file, contents of the file in one go. And the thing why I've mentioned this example is because we had a similar code that calculated the hash in our system that I worked on, and it was all pretty fine until we started to load the video. And when the video occupies like 1 gigabyte of memory and it is loaded inside the memory, that you start considering your life choices. So let's have a look. What is the actual difference? Why is the difference in allocation that impressive? I've taken the reference source from the GitHub. It's taken directly from the GitHub, and you can see how actually computing hash is implemented for the stream. So what happens here is that we're renting the array from RAID pool with 4 kilobytes of size. This actually just allocating the array with a bit fancier approach. Okay, and we're reading from the stream chunks of 4 kilobytes actually, and writing them in this buffer. And for each chunk, we are calculating the part of the hash. Then we return again the array to the array pool, and we assemble the hash from these chunks. So actually, this is what I've told. This is actually again batch processing, which can be done when we are dealing with streams instead of entire contents of the file. Okay, let's move on to another concept. And this concept is data structures. So again, a couple of months ago, I had an interview with a prospect, and I was asking him about different complexities of different data structures, and his answer was similar to, I can look up that in case I will need to look up that. But the thing is, it's not something that you have to look up. It's something that you have to understand in order to write better code. And I'll show you another one example, which actually forced me to revelate my stance towards data structure from the similar stance towards actually understanding the reasoning behind them. And that example is based on the fact that when you're using the dictionary or the hash, lookup by the key is way faster than when you're seeking an item inside the array. And let's have a look at another example which highlights exactly this concept. Okay, Let's run the benchmarks again. Here are the benchmarks. Let's close this stuff. So, data structures. What happens here is that we have sort of data storage. That data storage contains 10,000 of items, and these items are pretty straightforward. They have the key, and they have some random number of documents associated with that key. And the other thing that we have is the rule engine. The rules are pretty straightforward. Each rule contains the key of the aggregate item which they're applied to. You can see that the key here is random, so some items can have multiple rules, other items can have no rules. Each rule has an operation, and each rule has an operand. So let's have a look how the individual rule is applied to the item from the data storage. Here it is, apply rule to bucket. Nothing too fancy here. We just check in the operation and we'll do the addition, subtraction, multiplication. Pretty self-descriptive, I guess, at that point. So the point here is that we have two ways to deal with the things. One of the ways is that we can just load all the items. There's not too much of them, just 10,000, and we can pass them directly inside the rule engine for the rules to be applied to those items. And the other way, how can we deal with that, is we can convert them to dictionary beforehand when the key is our key. And then again, we pass that to rule engine. We have the overload, which accepts the dictionary. So what is the difference between these two methods? The one is that we're iterating all the rules, and we are trying to get the bucket which is suitable for the corresponding rules. And here we are doing lookup with the linear time, because basically a read-only collection, whether this is a list or array, this is the same data structure. This is array, and in order to find the item inside the array, you have to do lookup in the linear time. On the other hand, where you're dealing with a dictionary and when you iterate in all the rules and where you're trying to find the necessary bucket, you just trying to get this by key from the dictionary. And this is the constant lookup time. But whether this really makes any difference in the real world example, let's find out. The benchmarks will tell this. Okay, they're just about to finish. And you can see that the difference really exists at this point, and the lookup by the dictionary is almost 10 times faster, which again proves the point that you have to leverage the knowledge of the data structure in order to write better code. And again, if you will revisit our caching example, you might find that we are using HashSet for our cache, just for the same reason, because when we want to get the item by the key, we want to do that in constant time instead of linear time. So again, for example, when you're implementing your cache, you also have to take advantage of the knowledge of data structures. So these are my couple of words for you about the importance of data structures. And the other thing I wanted to mention is the SpanT. I already had a presentation on that, so I won't talk into details about it a lot. But the key thing I wanted to mention that this feature combines actually two features. One of them is that it's high performance API, and the other one is that it's quite enjoyable to read. And the thing is that you should follow the updates, you should follow the new stuff, you should be curious in order to find such things and implement them in your code. And such things won't have too much drawbacks because they are both pretty easy to understand and they can improve your code. And this is all about the coding for today. And the last but not least thing I wanted to mention is that, as you may have heard the news, there's a full-scale Russian offensive going on here, and the outcome depends on the people of goodwill, not only on Ukrainians but on the all people of goodwill. And at this point, in case you were wondering how can you step up and you didn't know how, here are some ideas for you. The first one is the official government page. I'm supporting Ukrainian military via this page myself since the full-scale invasion broke out, and the other two are non-organization, but they are also pretty reliable. They are working for 8 years since the war in Donbas region broke out, and I also have been supporting this organization for 8 years. So in case you want to step up, you can do that as well. So I've done with my presentation. I'm really thankful for your attention, and that's it.
Wow, Bodan, that was a very long and a very detailed session, I would say. It went over my head. I'll be very honest. I couldn't get most of it because I'm not a lot more into this microservices and performance testing and all. But I saw there were like little too many slides, Bodan, right? So how long? I know all those code samples and all those best practices that you have shared with us today. It has come from your day to day working with different projects. But how long did you took you to go ahead and build that presentation?
Oh, actually, the thing is with this presentation that I've compiled it from the multiple articles.
Mm-hmm.
You know that the thing is that there are a lot of tiny advices that are gathered here and there, and if you look at each advice into the detail, it looks like it's not enough for the entire presentation because it doesn't look that advanced and that sophisticated. But when you gather all these examples inside the single presentation, yeah, of course, it might be a lot of information. But again, these things are not that complicated. They're more about the discipline and about basic understanding. And in case someone wants to have better understanding of that concepts, again, there's the link on GitHub inside the presentation, which will help to understand better what I mentioned here.
Okay, well, I get it. Over time you go ahead and build those presentations. That's how also it helps, right? Quick question, my more than is microservices are a hot topic now. I mean, people are also not talking just about microservices, but I was in one of the conference. They were talking about micro front end frameworks, right? Even that's what people like to go ahead and learn these days. So you working on microservices, what is one thing you find it very challenging or you find it a little tough to cope up with?
Maybe the most challenging thing, the correct way is talking about microservices is that each team owns its microservices. So
Hmm.
basically, to do the microservices correctly, as all the agile books tell you, your code structure should follow your organizational structure. Actually, this is called the Conway's law. But when you're working in a small scale company and sometimes you have to extract these microservices in order to scale different parts horizontally, it might happen that you have more microservices than actually team members if you're not careful enough. And for example, if you need to test a bit more complex feature and you need to test this feature, you have to spawn multiple microservices and they are occupying quite a lot of resources on your machine. This is one of the challenging things. I guess this more organization. And another thing is worth mentioning that when talking about microservices in presentations or in articles, people omit important stuff which is might be not be necessary for presentation, like login, like observability, and sometimes people might have a vision that is not important for the system, but this is crucial. And for example, such thing as distributed login, in order that you have a trace across all your system, across all your microservices, is another thing which is worth realizing, and it requires certain organizational capability in order to implement correctly.
Yeah, I mean, I find it humorous when you say there might be more microservices than your team members. So, Bodan, that was a really great presentation, Bodan. I mean, once again, thank you so much. Is there anything you want to plug in before we end the live show?
Uh, no, I guess I've said everything that I have to. But again, if this is the word to the viewers, in case you're feeling the same way as Simon and you feel a bit overwhelmed, don't be shy to look at the codes. Don't be shy to investigate more about each concept, because these are things that you more likely encounter in your database. It's not something like some rocket science that only top performance do, and these things might really save your life, save your professional life.
Yeah, Bodhan. So I would say thank you so much for being a part of C Sharp Online, contributing to the platform. Your articles and all the contribution that you do really help other folks who go ahead and read it. So thank you so much for being such an important part of our community. We would love to have you back. Most probably this time in person, I get to see you, and then we do one of these shows. I'm definitely looking forward to it. Thank you so much once again. I know it's evening time. We like to go and spend some time out or maybe with family. So thank you so much for the once again. And yeah, see you soon. Ta-da.
Thank you as
Bye.
well. Thank you as well. It was a pleasure for me.
Thank you.
Bye.